the first heavy fermion superconductor had been discovered a few years earlier, his addition of these new uranium-based superconductors really allowed the field of heavy fermion superconductivity to explode. But his interests actually, as far as I can tell, date back to his days as a graduate student with Bernd Matthias. And Zachary, please correct me if I'm wrong, but I believe your second publication as a student was on rare earth impurities in yttrium B6 and zirconium B6, where he showed, among other things, that cerium impurities in yttrium B6 produced a Kondo impurity effect in the resistivity and a rapid suppression of superconductivity. And this, I think maybe the next year, a year after, you discovered this large zirconium isotope effect in zirconium B12. So that's sort of ancient history. In the mid-70s, Zachary's attention turned to intermetallic superconductors, where, among other things, he pointed out that this unusual saturation in their normal state resistivity corresponded to an electronic mean free path that's comparable to an interatomic spacing. And then in the 1980s, Zachary's work on heavy fermion superconductivity was interrupted by high TC. And even in that era, he was the first to discover high TC superconductivity coexisting with antiferromagnetic order in the rare earth barium-2 copper 307 system. And that discovery clearly pointed to the role of copper oxygen planes in producing the high TC. And of course, more recently, there are his discoveries of superconductivity in ytterbium aluminum boron 4, and of course, the cerium 115s that have received so much attention. So the field of superconductivity and superconducting materials, I've just touched on a few of Zachary's contributions, but his fingerprints are all over the field. This imprint has come from his keen physical insight as well as his just ability of black magic to produce the highest quality samples, often in single crystal form. So Zachary, we're looking forward to your insights on the systematics and superconducting materials. So it's all yours.
Okay, thank you, Joe, for that that overly flattering introduction. I should say that this particular thinking about systematics of superconducting materials has been kind of an ongoing project for quite a while, and the people that I've talked with about this and gotten input from are both you, Joe, and Priscilla Rosa, and my old-time friend Hans Rudiat. So so let me see here. Oop. So let's see, I'm having trouble advancing this thing now. Oh, here we go. Okay, so the question is that I'm interested in is, can we say some general things about where to find superconducting materials? And of course, we know that superconducting materials they're widespread across the field of intermetallic compounds and related materials. And what I hope to cover is to say something about what we've learned from heavy fermion superconductivity, which in my view gives us a kind of an insight very generally into superconducting materials, and eventually one of the points that I'm interested in is the fact that a lot of superconductors happen around the materials that satisfy intermetallic compounds or metallic compounds satisfying valence rules, which is not the usual thing for metallic compounds. Okay, so one should probably start in talking about superconductors with the elements. And I just show this this ancient Matthias type diagram. This is what things looked like when I was at the end of my graduate student years, which is actually half a century ago. And this is Matthias's standard periodic table that he always showed, which shows the superconducting elements, the magnetic elements, and the ones that become superconducting under pressure. So the modern version of this is from Jim Schilling, actually shows the, we have here the, I don't know if my pointer's visible or not, but you have the superconducting elements that are superconducting at normal pressure, and then you have the ones that become superconducting under pressure. And you see that actually well over half of the elements are actually superconductors. And of course, that's a much higher percentage than you find in intermetallic compounds in general. But of course, what you can say about this is that the ones that become superconducting under pressure, in fact, are usually not in the crystal structures that they are found in at ambient pressure. So another way to look at this diagram is in terms of what the superconducting temperatures are, and this is some scale here for where color is supposed to be saying something about what the TC is. And if you look at this, there doesn't seem to be any systematic about where the highest TCs show up as you go across with, for instance, a variable such as electrons per atom that Matthias so liked to use for in the study of superconducting transition metal materials. It's also interesting to me the fact that, of course, the really good metals like copper, silver, and gold just are not superconducting at all. Pressure is not the only thing you can do with looking for superconductors. And here's, in fact, you can, in some cases, you can expand the lattices these days with a kind of McKenzie cell. But in fact, Paul Schmidt at Bell Labs years ago produced metallic films with so-called ion milling using the noble gases. And in fact, we have here that chromium becomes superconducting when you deposit it in this fashion. You get rid of the anti-ferromagnetism of chromium, and it shows up. And so you actually wonder about many other materials, if you could expand them, where you might go. So let me turn now to you know, my favorite field, the heavy fermion superconductors. And the point about these is that they're originally extremely rare form of superconductor, but suddenly at a certain point, it was realized, and Joe Thompson was one of the first people to realize this, along with Lonsrich and his people at Cambridge, that all the heavy fermion superconductors seem to appear near an antiferromagnetic quantum critical point. And another point in this that I'll discuss has to do with the fact that antiferromagnetism can coexist with the superconductivity, but in instances where, for instance, using a variable such as pressure, that when the superconductivity occurs at a higher temperature than magnetic order, you don't actually, when you have essentially a magnetic transition curve and a superconducting transition curve crossing, if superconductivity occurs first. In other words, at a higher temperature, you do not have a lower temperature magnetically ordered phase. And this will be, and this to me is a rather important point. So the first of the 115 materials that where superconductivity was discovered was cerium, rhodium, indium 5, an ambient pressure antiferro magnet around a little above 3.5 degrees. And this is the phase diagram on the right here, where with pressure, and what one sees is with pressure at a certain point, you start getting superconductivity coexisting out at pressures beyond roughly 1 gigapascal. And then at this point here, around 1.75 or so gigapascals, the superconducting curve crosses the TC crosses TNL, and beyond this point, there is no magnetic order existing out here, whereas over in this region at lower pressures, you have coexistence. And what happens here, we know from this high pressure de Haas-van-Alphen experiment from Onuki et al., that in fact, the Fermi surface changes as you go across this pressure. You go from a Fermi surface that is essentially the same at low pressures as lanthanum, rhodium, indium 5, to one at high pressures over here, beyond essentially this extrapolated so-called quantum critical point, which corresponds to a Fermi surface that is seen in the ambient pressure member of this superconducting member of this series, cerium, cobalt, indium 5, and so the thinking about this is that in fact the Fermi surface at this higher pressure region includes the F electron, the cerium F electron, essentially, whereas it does not include it in this low pressure region. And a further confirmation of this thinking is that, in fact, you can make the tetravalent thorium, rhodium, indium 5 compound in this structure, and it has essentially a Fermi surface that is quite similar to this high pressure phase. So that's also supports the thinking that the F electron is included within the Fermi surface. This experiments were done on thorium, rhodium, indium 5. Not so easy to make this material by the group in Tokai. So this is the phase diagram with pressure of this ambient pressure cerium, cobalt, indium 5, the sort of poster child in a certain way of heavy fermion cerium superconductors. And the interesting thing here is, to me, is that you have actually an increase in TC from about 2.3 Kelvin to about 2.6 Kelvin, somewhere around 1.5 gigapascals. Now, what happens when cerium, cobalt, indium 5 goes superconducting? There's this interesting, in this diagram over here, this is data from Stock and Broholm, that there's this neutron resonance develops when one passes through the superconducting transition temperature. In other words, there's some of the magnetic fluctuations get gapped out when cerium, cobalt, indium 5 goes superconducting. In the lower figure here, we have the specific heat shown. This larger curve is the ambient pressure superconducting transition for cerium cobalt indium 5, which has this very large anomaly. You're roughly, if you integrate the entropy here out to TC, it's roughly 30% of R log 2. At this higher pressure here, out essentially around the maximum in TC, you've lost roughly, you have about half the entropy that you had at the lower pressure. So over here on the right, these diagrams show one, the residual resistivity that one extrapolates from above TC for cerium cobalt indium 5 as a function of pressure. And this is essentially, there's an intrinsic residual resistivity in this material which disappears with pressure, essentially vanishing at this maximum where the TC becomes maximum. And and we also and so what seems to happen if you essentially you can make an estimate. That's as if what happens, what corresponds here to this establishment of the neutron resonance. We don't know what happens with pressure to this entity, but if you believe that the resistivity that one's losing below the coherence temperature in cerium cobalt indium 5, which is of order of 40 Kelvin, that corresponds to resistances would be approximately proportional to the amount of spin fluctuations that are present, then in fact this extrapolated resistivity here actually corresponds to something like 30% of the this magnetic spin fluctuation resistivity that exists at the coherence temperature, and this is disappearing as one goes down to with pressure here. And so the idea is that cerium cobalt indium 5 still has essentially some of this spin. Not all the electrons have been incorporated into the Fermi surface at TC. And what happens at TC in this material is that these spin fluctuations, these residual spin fluctuations, are gapped out by the superconducting transition. And this is just going some more data that has to do with this. Okay, what's the conclusion here? So the idea is that heavy fermions, the general picture is metals arise from a dense lattice of Kondo centers in which you have essentially the Kondo compensation competing with magnetic order, and that coherence is synonymous with the formation of a Fermi surface incorporating the F electrons. And the interesting aspect of the superconductivity is that part of what it can do is it can gap out part of the magnetic fluctuation spectrum. And this provides a competitive route for the loss of entropy at low temperature. Okay, now let's turn to other superconducting systems and see how the thinking goes, or my thinking, so-called thinking, goes here. And so we have this wonderful work that was done with the pnictides and the you know, the prime driver here originally was Wolfgang Yajko is the expert in pnictide chemistry. And we know that, well, let's see, the way this story goes is that there was a set of compounds that Yajko essentially designed, and they were of this of which lanthanide iron phosphorus oxide was one of these in this so-called zirconium copper silicon arsenic type structure. And Barbara Zimmer apparently did her PhD thesis on this. And one of the interesting things about this, well, an aside remark about this work, is that she knew in her work that that the lanthanum iron phosphorus oxide was in fact a 5 Kelvin, roughly 5 Kelvin superconductor. And this is not even mentioned in this paper that reports the discovery of this compound, which to me, it was thought to be uninteresting that that was so. And yet here's Hosono later on, you know, did this work with fluorine doping that in fact generated TCs eventually that in this class of materials that got up over 50 Kelvin. So you ask yourself, how is it that this high temperature, very high temperature superconductivity was not realized in this work? This is actually just the kind of a figure from Yajko's work and how he gets to this particular structure. And you essentially can think you're stuffing essentially a sodium chloride type structure, you get distortions, and you come over to this, eventually this structure that was where this whole pnictide superconductivity bonanza started. And related to this this material is the fact that in the thorium chromium 2 silicon structure shown over here, you have the same kind of transition metal pnictide layers that exist in this structure. And so most of the, or a lot of the research on these materials has been done in this this rather, what you might say, simpler structure, thorium chromium 2 silicon tube. But it's also interesting the fact, of course, that cerium copper 2 silicon 2, the original heavy fermion superconductor, is in this structure. So this is just another you know, ball and stick picture of this structure, this thorium chromium 2 silicon 2 structure. Essentially doing the pnictide materials work in this structure was started by Urent in Germany. But one of the points that I would like to talk a little about is the fact that there's this if you want this pnictide, this here in this structure, this would be the thorium atoms, this would be the pnictide, and this would be the transition metal. And it's this layer that's believed to be essentially the most, you know, essentially driving force in the superconductivity. It turns out that there's characteristically two different lengths that you get for this pnictide bond. There's a long length and a short length. You know, they're well separated. I think this was apparently first pointed out by Raoul Hoffman. And the idea is when they're closer together, you actually have a real bonding interaction. And when it's longer, this bonding is much less relevant. So some experiments that were done on this rather low TC materials that you have in the long length for this, in this particular, for these phosphides, the long lengths, you have superconductivity showing up. And for the short lengths, you don't get TC, at least not down to 0.4 Kelvin. And so the idea, and so my thinking about this is that when you have the bonding, you've satisfied some tension, if you want to call it that, in the material. The bonding takes away that tension that's existing here when you don't get the pnictide bonding between these layers. Another material in this class where that was studied under pressure was lanthanum ruthenium 2 phosphorus 2, and this is just a pressure temperature diagram. And what you have out here with pressure, this has to do with you know which direction you're doing the experiment in. But there's a collapse from what they call tetragonal to the collapsed tetragonal. Same crystal structure. It's just you've gone from the long bond length, phosphorus bond length, to the short. And this work actually followed on earlier superconductivity work, this done by Schilling, and actually Hoffman's a co-author on this paper, that this is a 4 Kelvin superconductor. Again, this is in the long, the long phosphorus distance. And with pressure, you go out to the point where it gets collapsed and superconductivity increases as you go towards making this distance shorter, but it collapses into this collapsed tetragonal structure and superconductivity disappears, sort of following this trend that we saw earlier in those lower TC materials. I'd like to make a few comments about magnesium diboride, this roughly 40 Kelvin surprise superconductor that Akamitsu discovered, and this is again thinking about what I would call intermetallic, if you want, materials that satisfy approximately a kind of valence rule. And within the Zintel way of thinking about materials, you look at this this diboride structure. It's called the aluminum diboride structure. That magnesium diboride, you have divalent magnesium, and you have these boron sheets that are essentially graphitic-like. And in the kind of Zintel scheme of thinking about things, the idea is that magnesium gives its 2 electrons, gives 1 electron to each boron, so to speak, and essentially makes turns boron into something looking like carbon. And so you have these, essentially these become sort of graphite type sheets, and you get with this on this although this metallic compound, of course, but you have some, it doesn't quite make itself into a semiconductor, but it becomes instead this this very interesting superconductor. There's another interesting kind of aside here from Jefferson's group in Lorena, where zirconium diboride in this aluminum boron 2 structure is not a superconductor. It's actually very, it's a very low gamma material for which some band structure reasons. And you can alloy it with vanadium. Vanadium also forms a diboride, which is not superconducting. and you can get a small amount in. You have to do this with arc melting. It turns out you try to do it with single crystals, and it's very hard to get it in. In other words, zirconium diboride doesn't like to soak up very much vanadium. You have to work to get it in there, and and this is just a lattice parameter versus vanadium content, and and what happens is TC, you go from essentially no TC, that's zirconium boron 2, to a TC of something like close to 9 Kelvin. And so again, you have this this non-superconducting sitting there, and you perturb it by forcing some vanadium in, and it suddenly becomes a 9 Kelvin superconductor. There are other compounds that sort of fit into this scheme of things, which are surprising. Namely, you take zirconium nitrogen chloride. This is a compound that where you have here you have zirconium nitride layers, and you have chlorine layers here, which are essentially van der Waals bonded, and it's possible to stick in between, intercalate in here various atoms, and as is typical for working with van der Waals bonded layered materials. They're actually fairly easy to intercalate stuff into these layers, and you and putting lithium in there in this material actually makes a 25 Kelvin superconductor. So you start with what's essentially a valence type compound with van der Waals bonded layers. You add some electrons to it, and it becomes a superconductor. So you can think about the cuprates in the same way, that with the cuprates, you actually start, well, with the classic one that Alex Mueller and Bednarz discovered, lanthanum 2 copper 04. You can look at this as copper 02 layers with lanthanum 2 O2 layers, separating them. And this starts out essentially as a non-conducting, something that satisfies a valence rule, and you're able, with doping into strontium into the lanthanum layers, you're able to introduce holes into this material, and this becomes, of course, the start of the wonderful field of high TC materials. Here again, you're starting with a valence type compound, and you're managing to get carriers in there, and this becomes a superconductor. And so this is, this is just a set of so-called, what I call valence materials that become essentially very robust superconductors. And and again, this seems to be a common theme for a certain class of interesting superconductors. So let me turn back to what was considered a high TC materials when I was a graduate student. This so-called A15 superconductors, niobium-3 tin and V3Si, for example, and eventually niobium-3 germanium and extrapolated niobium-3 silicon. And it turns out that in these materials, it was discovered there's I say Peierls type, it's not actually a Peierls type distortion, but I'll describe it. There's a lattice distortion from cubic to tetragonal above TC. And there's strong coupling of this soft lattice mode to conduction electrons. And again, there's, and I'll discuss this business of what happens when TC and this transition temperature crosses. So here's just a picture of this A15 structure. You have these chains. You have these chains of, say, for instance, in V3SI, silicon chains, 3 linear, mutually perpendicular linear chains of vanadiums, and these with a body-centered cubic arrangement of the silicon. So what happens when you cool down, it was discovered by Barrett and Batterman, that you get a tetragonal distortion above TC at low temperatures, and this is right where, you know, one of the chains expands and one of the other chains contract, rather, so it's not exactly spirals like, it's sort of spirals between chains, if you will. And this is a picture here, this data from Jim Schilling, where you have this so-called, what they call this Martensitic transformation, this cubic to tetragonal transformation as a function of pressure here. And this is TC from, in this crystal he had was a little below 17, slowly going up, coming out to this point here. And this over here on the right is what the lattice parameter looks like as a function of cooling down in temperature at ambient pressure between these 2 points. You see this lattice parameter changing here. And then coming with TC, below TC, you actually don't get much change. And you say, well, and so let me show further this data from Hans Ott. And this is actually the elongation that is found on cooling. And what happens is you come up to, here's TC here, this is in the 100 direction. And in fact, it goes absolutely flat. And so what happens is you do not actually have the change in the lattice parameter stops essentially at TC. And this is quite similar in, at least in my thinking, to what's happening in say in the 115s, where TC, the superconducting TC truncates the lattice change that's going on. It's as if in the A15s here, that the superconducting transition apparently essentially stops the further development of the lattice distortion. So let me go back to the 115s and point out a similar thing happening in these cadmium doped cerium cobalt indium 5 samples. Cadmium doping at low level actually reduces, this is actually just nominal concentration, it's rather small amounts of cadmium actually go in, that the TC is reduced, and then actually you go over more cadmium produces antiferromagnetism. But Michael Nicholas and his co-workers discovered that, in fact, if you look at one of these, an alloy here, where in the magnetically ordered regime of these materials, what happens is this is the development of essentially the order parameter here on cooling, and this is where TC happens in this material. And the order, magnetic order, stops developing. In other words, superconductivity cuts off further development of the order parameter there, you know, which to me is highly reminiscent of exactly what we were just seeing in the A15 materials in the previous slides. Another interesting material that was studied by John Serrao and Joe Thompson and others at Los Alamos is the amazing superconductor plutonium, cobalt, gallium 5, and these Migliori and Brad Ramshaw did this wonderfully ultrasound experiments, and what they discovered is they can extract out essentially the what amounts to a kind of a bulk modulus from these temperature-dependent elastic constant measurements, and essentially the bulk modulus essentially shows a softening, essentially following the Curie-Weiss type law on cooling to low temperatures that would extrapolate to, you would have to read the paper to see exactly how they extrapolate, how they get this data from, for the bulk modulus from these curves. But you essentially have a Curie-Weiss type law. It reminds one of what one sees in ferroelectrics, that extrapolates to a, if you will, to 0 at 9 Kelvin, and which is actually below the 18 Kelvin transition temperature. And so that it seems that what happens here is that the superconductivity, in this case, similarly to what we've seen in the previous examples, is to somehow quench this lattice softening and cooling down. Again, part of a very similar pattern in superconducting materials. And finally, I come to make a few comments about the hydrides, although my friend Jorge Hirsch does not believe that these are actually superconductors. If they are superconductors, and which most people believe, that the way I would think about these is that, in fact, if you, as one applies pressure to these materials, the competition that one's dealing with here is between between bonding and non-bonding with between hydrogens. This plot here is actually from this paper from Warren Pickett and co-workers, the so-called Levins-Carbot plot, where you have you take the area essentially of alpha squared f. This is for the hydrogen derived quantities, and you see that there's actually a rather interesting parallel between this area and TC, and you can think of this as what's happening, in fact, as having to do with a kind of competition between hydrogen bonds and not. So let me make some final remarks here, and one of them is that that has to do with you know, about one's materials savvy or smarts and raising TC, and in fact, it's not in general obvious where at the start one should look for TCs, you know, particularly, you know, the example in the pnictides where the chemists that really just know everything about pnictides you know, somehow it wasn't obvious to them what was really hiding back there, the potential that was hiding back there in these materials. And so those of us that work in materials have not always been so very clever about raising TC. So where are the superconductors? Well, for the heavy fermions, they're near magnetic order. You know, for high TC, they're near what I would call charge order, this valence electron precise compound type material. Near in BCS, near some kind of lattice instability. So the highest TC is found in proximity competing localized phases, both quite generally across all kinds of materials, as I would say. In the fact, superconductivity, you know, runs, does run in structures, and in a certain sense, the way I see it, it's like the thinking that, you know, if you think of that where physics turns into chemistry, it's sort of where banding and bonding, those kind of different views become relevant on either side of this divide. So what is this chemistry? Well, I regard it in a kind of backwards way, that superconductivity is there solving a problem that a kind of an unresolved tension in the electronics of the material. And then in fact, the superconductivity is in fact diagnostic of this kind of not so obvious problem. And so that we should, in some sense, when you find a superconductor, the interesting thing to try to discover is exactly what is the problem that's sitting there, and in a way that one can say that superconductivity is fundamentally a chemistry problem. And I think that's all I have. So thank you for listening.
Thank you, Zachary. Thank you very much. So, you willing to take some questions and comments?
Sure.
Sure. So, any questions or comments for Zachary? So Zachary, so superconductivity appears near some instabilities, the way you're thinking about this, is that right?
Yeah.
So are there other instabilities that we haven't considered yet that might lead to superconductivity, or we have exhausted those relevant instabilities?
Well, I mean, you know, when I say instability, for instance, sometimes you know that you're not always looking at a phase transition necessarily, although it's potentially one. I mean, for instance, we saw in the pnictides, you know, it's this bonding, non-bonding, although it's a very sharp difference between the two, you know.
Right.
But the but you know, in making, you know, in the formation of solids, you know, that one does not always have, how do you say, the solids are not always happy, so to speak. Right. And so superconductivity seems at the to be expressing that some lack of happiness, if you want to put it that way, in the materials. And so this can take many forms, I think, you know. Right. And so I don't quite answer your question.
No, but I get it. So someone has their hand raised, is that
Yes, we have one person. You can unmute yourself.
Okay. My question is about some materials that are loosely based on the same principles as cuprates, and in particular, I mean iridate, nickelates, and to some extent, for example, strontium rutenate. Do you have any opinion on the differences between the properties of these materials? Because, for example, in strontium iridate, despite it's being doped, I think superconductivity hasn't been realized, and nickelates realized only recently, and apparently it was quite more complicated path than in cuprates. And in ruthenates, the situation is completely different, so to speak. So is there any, like, some more detailed principles even within the same general series of compounds that you can think of?
Well, let's say you're so let me see if I understand. I mean, for instance, strontium iridate, strontium 2 iridium 04, right? Which is happens to be also in this same crystal structure as and the nickelate as the high T, as the lanthanum 2 copper 04, and let's see how my thinking about those materials in general, with so-called thinking, let me put it that way, is that, I mean, for me, they're quite unusual materials in that you have this charge separation between layers. When you look at them, you've got this, which is sort of at the start of the day, you have the transition metal oxygen layer, which is carrying a lot of negative charge formally, and the metal oxygen layer, the other layer, say lanthanum oxygen or strontium, what have you, positive. And so it's actually, to me, it's unusual even that you form a compound like that it's stable against splitting up into separate oxides. And so it's sitting there in a kind of unusual situation, it seems to me. So that, I mean, it's as if there's some kind of large Madelung energy that's between these layers, if you will, that's allowing this crazy properties that are coming out in these materials. So I just regard the what I would call the simplest picture of the chemistry of these materials is actually quite unusual. So that doesn't really answer your question, but that's how I think about what goes on.
Thank you.
So thanks a lot. I see that there are 8 hands raised so far, but I've lost track of who's next on this list.
Oh, it's in order. So the next one is Ivan Bozovic.
Hi, Zach. A question about cuprates. In cuprates, there have been like half a dozen of instabilities potentially competing or intertwined, at least a few of which are real. My question is, what in your thinking is the bad actor? Which of them is the one that is cut by superconductivity?
Well, I don't, I'm sort of an agnostic, or maybe not even sort of an agnostic on this. I think there's these materials, it seems to me there's many ways that they can go. There's, there is a tension that's sitting there. And so by perturbing the system, the layers or what have you in various ways, you can favor one kind of low temperature happening versus another, but that and so superconductivity is just one of the things that can happen at low temperature in these materials. But it's also, again, a diagnostic of the fact that there's that something's not quite happy in that structure or in general.
Thanks.
Okay, I think maybe Bhaskaran is next, is that right?
Is Ganapathy, yes. You can unmute yourself.
I have a short comment. Zach, I enjoyed your talk. And in particular, the last statement, that superconductivity is fundamentally a chemistry problem, actually tells about the tension between theory community in the field of superconductivity. Those of us who believe that we have to understand local bonding and chemistry, quantum chemistry, and then from there start some with relevant model and go ahead. And those of us who start with ab initio and forget about bonds but focus on bands. So your superconductivity is fundamentally a chemistry problem. It's a very encouraging statement to us. Thank you.
Thank you. So maybe Paul Canfield is next. Paul?
Yeah, thank you, Joe. Can I be heard?
Can you speak up, please?
Sure. Can you hear me now?
Yes, we can.
Lovely. Zachary, when you were talking about the pnictides, you stated that the sort of avoided transition is the collapsed tet. For some of the phosphides, I might agree, but for the iron-based ones, it really seems that the magnetism and the associated structural are the key avoided transitions for finding the max of TC. The collapsed tet, when it happens, just wipes everything out. But for the high TC, I would say it's the magnetism and the orthorhombicity. Do you have any comment on that?
Well, again, it's just always going back to Ivan's question remark. I mean, I think that in the what I would call in the non-collapsed phase, there's all kinds of things that can happen there. You know, that it's just I think there's in the landscape there's many things that are possible, and as and the phase transitions that are there that you mentioned, they're they're important part of that landscape up there, and what exactly happens, I think, depends on the chemical details of exactly how you've perturbed it.
Maybe we can move on. Thanks, Zachary. I think next is Warren Pickett. Warren?
Yes. Am I being heard?
Yes, I can
Yes.
hear.
There you, Warren.
Yes. Okay, Zach, right at the end, you mentioned the hydrides under pressure, metal hydrides under pressure.
Yes.
I just wanted to point out something that seems to fit in your picture pretty well. Your so-called thinking. A lot of us do some so-called thinking, and some of it's worthwhile. The hydrides are high temperature very, very high temperature superconductors, some of them, because their phonon frequencies are high. From calculations, and so far the lambdas are all from calculations, lambda varies from 1.5 to 2.5, something like that, whereas the calculated TC can vary from maybe 50 Kelvin to 300 Kelvin. So it's not a lambda feature, it's a high frequency feature, and that's understood from Ashcroft's work from when you were a kid. But I want to point out that as you are in the high temperature phase of, there are many examples of this in these hydrides, as you apply more pressure, the frequencies go up, of course, because you're reducing the volume, but in fact, TC goes down. And as you decrease the pressure, TC goes up until there's a structural transition. which limits the increase in TC, but the phonons are getting softer. And what happens is that there's a transformation to a phase crystal structure where you have hydrogen molecules instead of atomic hydrogen in the structure. And in other words, the electrons are becoming localized into hydrogen bonds, hydrogen molecular bonds. Mm-hmm. So this parallels several of your other examples, such as the cerium superconductors, where it's a question of localized F electron versus an itinerant F electron. So it's just another example of localization of electrons, mm-hmm. killing superconductivity.
Yeah, thank you. Yeah, Raoul Hoffman gave a lecture in Hemley's series last week, which where in a way he didn't quite get to really talking about superconductivity, but he talked about what happens at high pressures in these hydrogen compounds, and where you actually get changes in bonding as you compress these solids. But thank you, Warren.
So Pasquale, are you there?
Yeah, Joe, I'm here.
So I see we've run past an hour's time, so there's still several questions or hands raised. So what's your opinion? Is there a time limit here?
No time limit. You can go on.
Oh, great. Okay, thanks.
If it's okay with you and Zach, we can go
It's
on.
fine with me. It's up to Zachary.
Sure. Yeah.
Okay. So I believe
just one notice. We have 2 more questions after Daniel because they cannot raise their hands. So just to know.
They're in the chat.
Yeah.
Oh.
Yes, that's true. I cannot raise my hand. Yeah, sorry.
Okay,
Can I
don't
raise a
worry.
question?
I'll put you after Daniel.
Yeah.
Thank you.
Zach, as to your final conclusion that it's actually a chemistry problem, can I just very simply understand it in such a way that there is a tendency of electrons to form pairs, like singlet pairs spin up and down. But what is the fate of these pairs? Maybe they order in real space, and that will be simply valence bond solid, like hydrogen molecule, for example. Or they can be condensed in momentum space if by some reason it's not possible for them to form or not favorable to form really long-range solid state. Then they have a good chance to be mobile and then bother condense in momentum space and make superconductivity. Is it more or less like this?
Yeah, let's see, the
singlet pairs, which may be valence bond pairs or maybe Cooper pairs.
Mm-hmm. Yeah. Well, yeah. That. Well, I mean, you're reminding me a little of this. Your remarks remind me a little of this old remark, old paper from Marvin Cohn and Phil Anderson on where they were computing back in the 1970s what the maximum TC might be, and which came out to be in the 30 kelvins. But their comment was, of course, as you increase the electron phonon interaction, at some point you start to get something that's looking like a chemical bond. And
I think it's a different story, but they simply spoke about effective interactions that if Coulomb forces maybe overcome, direct Coulomb repulsion overcomes finally this electron phonon interaction. I think it's a different story. My simple naive picture is that if you increase coupling, then electrons want to form pairs. Okay, fine, but what happens after that with these pairs? That may depend on particular situations, and if possible, they form a valence bond solid, or if it's not favorable or not allowed, or you prevent it somehow, then they can remain mobile but still paired. Mm-hmm. That will be superconductivity. That's chemistry, actually. Competition with chemical bonds competing with mobile pair forming Bose condensate.
Mhm.
Is it what you had in mind as chemistry?
Yeah. Well, didn't, I mean, actually, wasn't it, I mean, this may not be exactly relevant, but, you know, Pauling's theory of the metallic state originally, he had a lot of trouble with intermetallic materials, and he actually worked on a theory with electron pairs, I think, in his trying to understand metallic materials.
Well, could be. I don't.
So as interesting as this discussion is, maybe we should move on. Zachary's going to run out of steam here eventually. So maybe I think Haihu Wen is next. Is that correct?
Macaria, yes.
Okay, thank you. Yes, I cannot raise my hand for some reason here on the screen. So Zach, Zach, very nice talk. My question is that on one of the slides, you list the cuprate.
So sorry, we've lost your connection.
Joe, maybe you should go back to the list while we wait for Wayne to get back. So next, Anatar, I think, right?
Right,
Anatar.
Hi, Zachary. Very nice. I had probably a little bit narrow question, and I came to it after this 115 conference. At some point, you, with Satoru Nakatsuji as the first author, suggestion description of the normal state of 115s as Kondo gas to Kondo lattice condensation. What is the fate of this? Because I never hear it recently being discussed, although it was based on very interesting analysis of the susceptibility, resistivity, and heat capacity data.
Well, okay. I'll just give you my current thinking about it. Has to do with, you know, what determines the coherence temperature, and it seems to me that the coherence temperature is being determined by the distance to the nearest crystal field, excited crystal field levels. In other words, as you cool down, the Kondo effect is you're trying to make block type states that include entanglement of the spin degrees of freedom of the F electrons with the conduction electrons, but this entanglement gets spoiled, or you say, or there's a finite lifetime to it, because you can excite to the next crystal field level. And so it seems to me that if you look at the available data with having to do with crystal field splitting, say in cerium compounds, that in fact the coherence temperature is always of order half the distance to the lowest lowest lying excited state. And so it seems to me that sets a kind of it's setting something that looks like a Fermi energy, if you will, for the low temperature state. I don't know if that. So that's my thinking about this establishment of coherence. And so you end up eventually, if you have, you know, that's sort of, you generate up to the coherence temperature, something like R log 2. And, you know, if you consider that the low temperatures, you're essentially looking at a pair of doublets, doublet ground state and a doublet excited state. You'd expect something like R log 2 to be developed over that temperature range.
Yeah, but you see, if you go from the low temperature side, so we see that resistivity, and especially thermal resistivity, is a perfectly tracked magnetic entropy. And I would say this is a property of magnetic scattering rather than any crystal field effects. So of course, this is at much lower temperatures. This is like 10 Kelvin or so.
Well, it's I mean, the magnetic scattering is I mean, it doesn't strike me as I mean, I don't see, actually, I don't quite see why that is. I mean, I think that what you lose in the establishment of coherence, you know, you lose essentially all the magnetic scattering and cooling down, right? And
well, I see it below TNL, it goes away. So in cerium, rhodium, indium 5. So I see that at TNL, I see resistance going down very fast, and it tracks what is left after partial integration of the moment.
Yeah. Yes, I mean, well, that's right. I mean, but I mean, you know, in cerium, rhodium, indium 5, for example, you know, you have only you know, you only up the amount of entropy generated up to the Néel temperature is about 30% of R log 2, right?
Yep.
So you've gone fairly far into the Kondo compensated dense Kondo state, except magnetism wins out at that particular case. So.
Can we continue this discussion afterwards?
Sure. Yeah.
Good idea.
Thank you.
So maybe, I think Igor Mazin is next. Is that true, Igor?
I don't know whether it's true or not, because in my screen, the order constantly changes.
Yeah.
So I don't know.
We're assuming you're
Let's suppose that's me. Yeah, this is just, before I just want to stress my support for Paul Canfield's comment. I think that generally speaking, yeah, there are different potential instability, but in this particular case, we have overwhelming body of evidence that magnetic order is the key player. But my main comment is about our first question. What kind of instability? I believe, I remember that some 50 years ago, well, maybe 30 years ago, we were talking about that. Daniel may remember at Lebedev Institute and Ginzburg group. And the conclusion was that, yeah, there's, as Zach said, sometimes materials are unhappy to be as they are. And if they're unhappy, that they are relieving this unhappiness in this most simplistic scenario, say too high density of states, through any mechanism that can be available. And as long as it happens, then no other mechanism is needed anymore. And there are only three orders in nature. There are two diagonal orders, charge order and magnetic order, and off-diagonal order, which is some kind of superconductivity. And then the question is, so this exhausts the list. The question is now, what specific order can, because there are tons of different magnetic orders, not necessarily antiferromagnetic, that could be spiral orders, toroidal orders, which at some point were very popular and then came back, and so on. There are charge structural transitions, there are charge density wave, all of them are possible, and there are different kinds of superconductivity. But the fundamental principle remains the same. There are three kinds of order through which the system which is unhappy in their current state can lower their energy. So I just thought that this clarification to the first question could be useful. That's all.
Thank you.
Thank you. So maybe before we get to Musio, if you don't mind, I think Haihu has been able to raise a comment, that they sent us a comment. His web is not stable, but his question is, so you sort of suggested that superconductivity cuprates is near some sort of charge ordering instability. The question is, would you agree that superconductivity in the cuprates has some association with anti-ferromagnetic order or anti-ferromagnetic spin fluctuations?
Well, yeah, yeah. I don't. Yeah, I don't have any problem with that.
Okay.
I mean, I'm just saying that I'm talking about how you take a happy material and make it unhappy. Then what you know, there are many channels open to it.
Right. Okay. So I think Musio Constantino is next. Musio.
Yes, here I am. Hi, Zach. Hi, Joe. Zach, you mentioned about this the superconductivity appearing these close to instabilities. I wonder if you think that the excitations that are associated with these instabilities, they are the one that provide the clue for the formation of the glue for the formation of the superconducting pairs. So near lattice instability, we would have phonons. Near magnetic instability, it would be magnetic excitations that would provide the clue, or CDW excitations in the case of a charge order instability.
Well, I don't have a good answer for that. I mean, one of the things, let's think for a minute about the beta tungsten A15 materials. You know, you can generate crystals of B3SI that where you don't always see the lattice distortion, where it's not very clear. And so the fact is that you say, you know, you might think that maybe TC would go up if you eliminated the lattice distortion, and I don't know that there's any good evidence for that, and so I don't think the answer to your question is simple.
Okay, thank you.
Amen. So are there any more hands raised that I'm not seeing?
We have two more questions because they cannot raise their hands. First of all, it's Christoph, and then we have one from Ben-Har. Christoph, please unmute yourself.
You hear me?
Yes, we can.
I have a question concerning niobium. There was a couple of years ago, there was a PhysRev letter showing some sort of lattice instability, Martensitic transition in high purity niobium. Has this been confirmed?
Let's see. Was that work that maybe came partly from Lorena?
It was partly Los Alamos, I think, and there's thermal expansion measurements from.
I see. Yes, I don't know the answer to your question there.
Okay. Thanks.
Ben-Har, you can unmute yourself.
Speaking. Hello?
Yes, we can hear you.
You can hear me. Yeah, I was just wondering with respect to the vanadium-3 silicon, where you showed that superconductivity exactly truncates the phonon softening. Is there a reason why it only truncates it and doesn't invert it? I mean, why does it exactly stop below TC?
I don't have I only have the observation. I think there's more to be understood there in exactly how how it does this, or even the example of in the 115s with the cadmium doped serum cobalt indium 5. You know, what exactly happens when you know, what is the real mechanism for superconductivity truncating the magnetic order, for example? In detail, I don't know that there's a good explanation for that.
Okay, thanks.
you. Is there any more questions for Zachary? He's been very hard at work here.
We have one from Prabhakara. If you want, you can unmute yourself. Okay, he has a problem with the microphone.
Okay.
Why we should
So maybe-
develop... Okay, I would read the question.
Oh, sorry, go ahead. Go ahead.
Sorry. Why we should develop different materials, and what is the roadmap for this field? Is it only for the advancement of the field, or if so, where we should concentrate?
Well, I'm not, I don't have a secret that I'm hiding here. I mean, I feel that, 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 you know, there's a deeper, there's more to be learned from superconductivity, I think, in terms of, it seems in many of these cases to be a much more strong coupling business. And so that one that, historically, at least in my limited understanding, one sort of doing superconductivity via some kind of perturbation theory. And a lot of what goes on strikes me as getting into a much stronger coupling and more interesting regime. And it seems to me that future developments would hopefully go in that direction. That there's a deeper way that we can think about superconducting materials. But this is just speculation on my part.
I can see one more blue hand raised. Frank, please.
Hi. That last response actually prompted me to ask this, and partly because your talk was such a nice overview. I just want to get your thinking, like the fact that you juxtaposed all these superconductors in one talk and talked about them in some way to unravel the mystery. Is that, should we take from that or are we looking for a unified mechanism that that sort of helps us understand superconductivity for all materials, as opposed to what's been happening in the last 30 years as we've been sort of compartmentalizing for, heavy fermions work this way, high TC cuprates work another way, and so on. What are your thoughts on that?
Okay, well, I'll say something that probably one should only think in the privacy of their own home, but or study. That, I mean, superconductivity is this wonderful macroscopic quantum phenomenon, and and in the privacy of my own home, I often think it's a kind of crazy manifestation of the particle wave duality of electrons, and I think I like to think about exactly how that works, and so not that helps, but yes, I think there's a much broader way that superconductivity showing up at this boundary, as I say it, between physics and chemistry and so on. It's really telling us something.
Okay, thanks.
Okay, we have no more questions.
Thank you. So maybe if we could unmute and thank Zachary for this very interesting and obviously stimulating talk. Thanks a lot, Zachary.
Thank you, Zach. That was great.
Thank you.
Hey, Zach, thank you very much. So could you please stop sharing the screen for a moment?
Yep.
Okay, so before we finish, I would like to ask all of you in the audience to start your videos so I can take a very nice picture of the audience of today. Okay, it's very nice seeing you all. So we start taking the pictures. So my first screen, 1, 2, 3, print screen. Okay, that's perfect. So thank you very much. Thank you, Zach, again. Thank you, Joe and Maria, for helping me sharing the section. It was very nice seeing you all, and I hope to see you next month for the next SCES webinar. So thank you. See you.
Thanks, Pascal.
Bye-bye.
Thank you.